So chapter 2. Okay, chapter 2. We're going to study unsaturated hydrocarbons. Okay, unsaturated hydrocarbons. So first, let's take a look what we already done in chapter 1 for classifying hydrocarbons. Okay, for classifying hydrocarbons. We know hydrocarbons are the simplest types of organic compounds. They consist only of what? Two elements, right? Carbon and what? Hydrogen. Those are called hydrocarbons. And in chapter 1, we already completed those hydrocarbons containing only what? CC single bond. Okay, CC single bond. Now, CH is always single bond, by the way. But what we focus is carbon-carbon, how carbon-carbons are bonded together. And those hydrocarbons are called alkanes or saturated hydrocarbons. Okay, saturated hydrocarbons. This chapter, we're going to study 3 types. Okay, 3 types. Focusing on this type, of course. 3 types of hydrocarbons containing CC multiple bonds. Okay, mainly is CC double bond and CC triple bonds. Okay, and very special types of unsaturated hydrocarbons called aromatics. So those are the 3 types classified as unsaturated hydrocarbons. Okay, unsaturated hydrocarbons. And we're going to answer the question some of you might have or had is why we call those unsaturated. Why we call those saturated? What is saturation and unsaturation means? We can answer that after we study this. Okay, so first let's take a look at unsaturated hydrocarbons. What are they? Okay, what are they? The first type of unsaturated hydrocarbons are the ones containing carbon-carbon double bonds. Okay, carbon-carbon double bonds. Okay, and when you see a CC with 2 lines, means there's a double bond. We call those unsaturated hydrocarbons alkenes. Okay, they end with E-N-E. Okay, E-N-E, alkenes. And then we're going to briefly talk about hydrocarbons with carbon-carbon single bond or triple bond. Again, you don't need a lot. As long as it contains 1, then we call those hydrocarbons what? Alkynes, end with Y-N-E. Okay, Y-N-E, alkynes. Like I said, in the second half of this chapter, we're going to discuss hydrocarbons with this ring system. Okay, with a unique ring system, which looks like an alternating double and single bond in a 6-member ring. But again, we're going to discuss what makes these structures unique. Instead of classifying them as alkenes, why we classify them as a separate category? We call them aromatics. Okay, we call them aromatics. So these are the 3 compounds, and those are the simplest alkenes, alkyne, and aromatics showing their structures in their complete condensed, like expanded structures. This is the 2-carbon alkene. Remember, you at least do 2 carbons, right? 2-carbon alkene. This is the 2-carbon alkyne. Here, the carbon is not shown here. This is a carbon. That's a carbon. This is the 6-carbon aromatics. Again, these are the simplest, 1 in each category with their structures and of course their names. Okay, with their names. Good so far. So these are the topic for this chapter. Let's take a look. What's going on for a carbon? Okay, what's going on for a carbon when it is involved in CC double bond? Before we do that, let me ask you guys, we studied in chapter 1, when carbons are involved in single bonds. Okay, when carbons are involved in single bonds, what's going on with that carbon?
4sp3.
It is what? Hybridized into what? 4sp3 what? Orbitals. Is that right, guys? Each carbon contains what? 4 sp3 orbitals. Each sp3 orbital contains a what?
1 electron.
1 single electron. This is what a carbon looks like when they're in organic compounds involved in CC single bond, in single bonds. And these 4 sp3 orbitals took the geometry of what? Tetrahedral. Okay, that's what each carbon looks like. Okay, in most of the time, if not involved in double bonds or triple bonds. Now, for carbons that are involved in double bonds, take a slightly different types of hybridization. The same, this is a carbon. Okay, this is a carbon. These are the bonding orbitals involved in chemical bondings. There are 4 electrons. Okay, 4 electrons. Those 4 orbitals, remember when they're sp3, all of them will be used for mixing, like your cookie doughs, all of them used for mixing. But in this case, when carbons are involved in CC double bond, only 3 of them, okay, this one, 2 of those, doesn't matter which 2, 2 of those plus an S, 3 of them are used for mixing. Again, we call that hybridization. So 3 are used for mixing. You end up with what? 3 new ones. You start with 3, you end up with 3. We call those 3 orbitals sp2 orbitals. Okay, sp2 orbitals. Why we call sp2? Because you only use what? 2 of those p's. The s is always used. So s what? p2. 3 of them. And we know that the other one is not done anything. It just left behind. So there is 1 p not doing anything. But after that, still you got 4 orbitals. Each one contains what? A single electron. Okay, single electron. We call that, sp2 hybridization. This is what the carbon needs to be done. Okay, it needs to be done when it is involved in double bond. Okay, in CC double bond. The hybridization type is called sp2. What is sp2? 3 s2p orbitals plus a what? Unchanged p orbital. Each one has a single electron. Okay, now you may wonder what those 4 orbitals look like. Okay, we know 4 sp3 look like what? Tetrahedral, right? Like this. This is what sp3 looks like. So what does the sp2 carbon looks like? It looks like this. Those 3 sp2s are arranged in a planar geometry. They're all in the same plane. Do you see that, guys? In the same plane. And because the total circle is how many degrees? 360 degrees, right? If you walk around the circle. So each sp2 and sp2 between each other has what? 120 degrees between each other. This is what an sp2 look like. Do you guys see that? We call this geometry trigonal planar geometry. Okay, trigonal planar. Do I have it here?
No.
Okay, that's fine. Just planar geometry. Why I call trigonal planar? Take a look. If I link those 3 dots, what's this shape? It's a triangle. Is that right, guys? Take a look. If I link all 3, is that a triangle? So this is a trigonal planar geometry. What does planar mean? Those 3 are what? In the same plane. Look. If I look from here or here, in the same plane. This is a carbon. My hand is a carbon. Now remember, there's 3 sp2s. 1, 2, and 3. Those light greens. See, in the same plane, like this. One of the not changed p orbital, the one that has nothing to do with it, that's left behind, still has 1 single electron, is perpendicular to the plane, like this. Okay, passing through, not just both up and down. Okay, it should be like this. Okay, passing all the way through, like here. You guys see that? Like this. Does it make sense, guys? This is a 3D model. This two, they're the same. Whichever you find is easier to understand. Okay, this is what a carbon looks like when it is involved in a double bond. Does it make sense? Good? See that? All right? Now, next, let's take a look. How does a carbon, I mean putting on the desk, so you guys can see. If you cannot, you can stand up, okay? You can stand up if you cannot see my desk, because I cannot hold both together. Can you guys see it on the desk? Okay, this is a carbon. This is another carbon. Remember, if you want a double bond, you need how many carbons? At least 2 carbons to make a double bond. So this is one of the sp2 carbon. This is another sp2 carbon. They're both what? Plane. Is that right? On my desk is a plane. When they're approaching each other, this sp2 and this sp2, they are going to what? make a bond. Do you see that? Like two heads bouncing together, end to end. They're making a bond. Meanwhile, this guy and this guy, they're both perpendicular to this plane. They're going to what? Make another bond. You guys see that? One approaching is what? End to end, like two person head to head, collide each other. Another approaching, what is it called? What do you think it's called? Like two people are what? Side by side, is that right?
Parallel.
Called a parallel. Okay, called a parallel. So this is what happens when two carbons are making a double bond. Take a look. This is the sp2 I'm showing here. You see that? They're bouncing what? Head to head. We call this bond, okay, we call this bond a sigma bond. They're end-to-end overlap. We call this bond a sigma bond over here. Okay, sigma bond. This sigma bond over here. You guys see that? sp2, they're what? Sigma bond. You guys see that? Now when they're making a sigma bond again, these two, like pillars, they are also going to what? Make a bond. But when they make a bond, they're not end to end. They're what? Side by side. Okay, they're side by side. The bond here, side by side. You see these two? Side by side. Make a bond called a pi bond. Okay, got pi bond.
Is the pi bond weaker than the sigma bond?
No, just two types of bond. Two types of bond. So what is a double bond? A double bond is a what? Is a sigma bond by what? One sp2 and a what? Another sp2. And a what? A pi bond by a p and a what? Another p. Okay, another p. Even though here you see two bonds, you don't see which one is which, but you know a double bond. These two bonds are different. One is what? Here, the pi. I'm sorry, the sigma. Another one is what? The pi bond. The pi bond. And somebody want to ask, well, what about the bond between C and H? All CH bonds are always sigma bonds because they're still what? End to end. Okay, this hydrogen is a ball. So think about anything bouncing to a ball can be assumed as what? End to end. So all CH bonds are sigma bonds. Sigma bonds. Does it make sense, guys? Okay. Again, you don't need to describe to people. Okay, it's not required for you to describe what is really happening between two carbons like this. All you need to know is a few take-home notes. First is what happens to a carbon in a double bond? Carbon is sp2 hybridized. Okay, what sp2 hybridized? The first thing, okay, carbon is sp2 hybridized in double bond. Let's first take home note. Number two. What does an sp2 carbon look like? It's what? It's a planar structure. Is that right? This is what sp2 look like, planar structure. And number three, most importantly, when two carbons in sp2 hybridization approach to each other, they will form a what? A sigma bond and a what? And a pi bond. What is the difference between these two? Sigma is between what? End-to-end approach, overlap. Pi bond is what? Side by side, parallel overlap. Okay, these two bonds are different. That's it. You don't need to know all the details about it. So what is a double bond? A double bond is a sigma and a what? And a pi. Okay, and a pi. Here is the showing the pi bond. Okay, pi bond you can use the symbol like pi, the mathematics symbol pi. Okay. And finally again, double bond, a sigma and a pi bond. This is the Greek letter for sigma. Okay, sigma. So here we have what? Two bonds. A sigma and a what? And a pi. And how about these bonds? They're all what? Sigma bonds. All single bonds are sigma bonds. You can even say that. A double bond normally contains a sigma and a what? Okay, they're different. Okay, they're different. All right? Any questions? Arvin, again, you can use pens. You can, two-person can help. Can see how they're approaching. Okay, if you have two hands can hold, you can see that, right? sp2 what? Sigma, and the PNP what? Pi bond. And hydrogen is like this. This is sp2. Hydrogen is approaching like this. Sigma, because what? This is a ball. Hydrogen is a ball. The head, you can say anywhere is the head for a ball. So there's still end-to-end overlap. Okay, that's alkene. Now before that, let me build a model for you. Okay, build a model for you. What does that alkene look like? Okay, let me build a model for you. Okay, because I make a double bond, so I need the springs so they can kind of like okay. Hydrogen. Okay, I don't put hydrogen on these ones, but you can take a look. Each carbon is what? Trigonal planar. You see that? This carbon is what? Trigonal planar. If I put this whole molecule on my hand, they're all one on the same plane. You guys see that? These two carbons and these four hydrogens, if there were hydrogens, they're all on my hand on the same plane. Why? Because sp2 carbon is what? Is planar structure. So both carbons and these four hydrogens should be on the same plane. Okay, should be on the same plane. If you have more carbons, they may be not, but these carbons, these atoms, all should be on the same plane. Why? Because this is sp2, that's sp2. They're all what? Plane. Does it make sense, guys? Okay, that's what this looks like. Okay, you can see all these atoms should be on the screen. They are on the same plane because this is sp2. That is what? sp2. Right? Next, naming alkenes. Okay, naming alkenes. Okay, and now when we study this, you will see why I mentioned in chapter 1, you learn the system, and then here you only need a few modifications. Okay, modifications. So when we name alkenes, the rules are very similar with a few modifications. The first modification is when you find the longest chain, you must include the double bond carbon in the longest chain. Or you should say the longest chain must include what? The double bond two carbons. Does it make sense, guys? Okay, for example, this molecule, they're the same. Even though this is the longest carbon, 1, 2, 3, 4, 5, 6, but this is wrong. Why? Because the double bond carbon here is not included. So we do not choose this name. We choose here. Longest chain is what? Here. You guys see that? Now after you find the longest chain, the same, you name the chain. 5 carbons. The prefix is pent, but this is double bond. So instead of calling it pentane, we call it pentene. You guys see that? Change the suffix from ane to what? To ene. So that's the name, the last word for the name, pentene. Again, the same, you draw a pencil here, cross it, pentene, done. This 5 carbon is called pentene. Okay, next. Another modification, very important, is you number the longest chain. Make sure the double bond 2 carbons get the lowest number possible. We're not talking about branches. We're not talking about groups. We're talking about these 2 carbons of the double bond get the lowest number possible. Here, you can see that. 2 ways for numbering it. I picked this one because what? You get 2 and 3 instead of what? 3 and 4. Does it make sense, guys? Yeah. Same here. Okay, same here. Both are 2 and 3. In that case, I need to consider there's a group on this carbon, so this carbon start with what? Start with 1. Okay, the rule is the same, gets the lower number, but you first need to make sure the double bond takes the priority, gets the lower number first. If, like this case, both numbering from left to right, right to left, double bond, both get the same numbering, then you consider what? The group. Does it make sense? Yes. We had a question.
That was my question.
Good.
Thank you.
Does it make sense, guys? Okay, but who takes priority? Double bond. In this case, they're both 2 and 3. Of course, you need to consider the chlorine. Then whichever chlorine is at, this is number 1. Okay, make sense? That's how you number it. Then, also very important, after you number the chain, use the lower number of the double bond to locate the double bond. Use the lower number of double bond. What does it mean? Double bond, how many carbons? 2 carbons. So these 2 carbons get how many numbers? 2 numbers. 2 and 3, 3 and 4, 5 and 6, doesn't matter. Then you use the lower number. For example, here 2 and 3. Lower number is what? 2. Then you use that 2 to locate the double bond. 2 butene means what? The double bond is between what? 2 and 3. Okay, the name is butene, 4 carbons, but you need to locate it. Okay, locate it. And the rest of it is the same as we learned in chapter 1. Okay, take a look, guys, if you understand the names showing this picture. Okay, I give you a few modifications. The first modification is what? Longest chain must include what? Double bond. The function double bond. Number 2, when you number the longest chain, make sure the double bond gets what? The lowest number. Number 3 is when you name it, make sure you use the lower number of the double bond, 2 carbons, to locate where the double bond is. Okay, locate the double. So that means when you name alkenes, there will always be a number. Do you see that? In front of the alkene name. That number tells people what? Where the double bond is in the chain. Does it make sense, guys? And the rest of it is the same we learned in chapter 1. Take a look. Any questions, feel free. Don't be shy. People won't laugh at you.
So in the previous example, when we did pentene, we did not say one pentene.
That one we're not there yet. That's what we didn't say. Correct. Okay, if you want to name this one, the name of this guy will be 1 pentene. She's right. This is 1 and 2, right? So the last name of this molecule will be what? 1 pentene. This is an ethyl group, so this molecule should be 2-ethyl 1 pentene. Okay, 2-ethyl 1 pentene. If you name it. Okay, take a look, guys. Again, anything, feel free to ask about these 4 names. First, you understand them. Then after you go home, you cover it, try to name it again, right? 3 times. If you name it 3 times, you can get it right. I think these are good enough. You had a question?
Do we not put these in alphabetical order?
What do you mean?
Like, in chapter 1 when we...
Yeah, if you have multiple groups, you do.
Okay.
These only have 1 group.
Yeah.
You don't need to worry about.
Okay.
Yes. If you have multiple branches, multiple substitutes, yes, the same alphabetical order. Okay, the system is the same. Here I'm only showing you some modifications. What's different? The difference is the longest chain must include 2 double 1 carbon. The name, of course, end with what? E and E. And then, when you number it, make sure these 2 guys get the lower number. Then you consider the groups. And finally, don't forget that number. Okay, don't forget that. You guys good? I think you're great. You're smart. You don't have a lot of questions, or you just don't want to ask. Anything? About these 4 names at least. All right. I give you a few minutes, 2-3 minutes. Name these 2 alkenes. Okay, name these 2 alkenes. You draw the skeletal first one, the second one later at home, okay? It's easier. But name those 2. I'll come around and take a look whenever you're done.
So 4-ethyl 2-pentene. So
4-ethyl 2-pentene.
the
The first one. Do you guys agree?
Yes.
Yes? You're sure? 4-ethyl 2-pentene, what she said. Let me write on board. first molecule on the left is 4, what? Say again. Ethyl 2-pentene. Someone said she was correct. Anybody else? No? All agree? Okay, unfortunately she was not right. Okay, the longest chain is not 5. The longest chain is what? Take a look. 1, 2, 3, 4, 5,
Or 6.
6.
Hexene.
Okay, so the last name is not pentene, is hexene. Okay, hexene. Now, like I said, when you draw the longest chain, after you find the longest chain, use your pencil to mark it. So whatever is not on the longest chain is which guy? The methyl group. Do you guys see that? So what's the name? Where's the methyl? 1, 2, 3, and what? 4. So the name should be 4-methyl
2-hexene.
2-hexene.
The second one is 3,3-dimethyl 1-butene.
1 second. Do you guys agree? The name of the first molecule? 4-methyl 2-hexene. Okay, the longest chain has to be longest chain. You include these 2 carbons, fine, but you have to find what? The longest chain. Okay, it's 4-methyl 2-hexene. Okay, 4-hexene. Okay? The second molecule she said, say it again.
3,3-dimethyl
3,3-dimethyl
methyl 1-butene.
1-butene.
Butene.
You guys agree? Dimethyl 1-butene. You guys agree? Okay, let's take a look. What's the longest chain? 1, 2, 3, and what? 4. So the longest chain is 4. And the double bond is between what? 1 and 2. So 1-butene, correct. And then those are 2 groups. In the parentheses, both are on which carbon? Which carbon?
Third carbon.
Number 3 carbon. You guys see that? This is 1, this is 2, that's what? 3. So 3,3-dimethyl 1-butene. That's correct. Okay, by the way, the skeletal structure of this molecule is this. Okay, it's this. See that? 1, 2, 3, 4. 2-methyl on the 3rd carbon. That's what skeletal structure looks like. Okay, you guys practice the bottom one, drawing the structure. Okay, I can take a look if you want later after you're done with practice. Okay, next. Okay, next. The double bond. Okay, the double bond does not have to be in an open chain. Can be in a ring. Okay, in a ring. And we call those molecules cycloalkene. Okay, cycloalkene. Why? Because they what? They have double bond. Okay, of course this molecule, okay, extremely unstable molecule with 3 carbons, should be named as what? Cyclopropene. Okay, propene. Again, end with what? E-N-E. Cyclopropene. Okay, cyclopropene. When you name cycloalkenes, okay, when you name cycloalkenes, you don't need to locate the double bond. Okay, when you name the cycloalkenes, you don't need to locate the double bond. The reason is, we know ring is the longest chain, right? The double bond always get what? 1 and 2, is that right? Because that's what you take priority for. So these 2 carbons is always what? 1 and 2. If that's always 1 and 2, you don't need to tell people where it is. So the molecule, this is called cyclohexene. You don't have to tell people 1. Why? Because this is 1 and 2, we know that. Okay, there's no confusion here. The same here. Okay, if you have a group, the double bond still takes 1 and 2. Then you either go clockwise or counterclockwise so that the group gets what? Lower number. Right? 1, 2, 3, and 4. So the guy is called 4-methyl cyclohexene. Still, I don't number these two. Why? Because they're what? 1 and 2. Okay. You just do counterclockwise or clockwise so that you meet this group the first encounter group, the lower number. Okay, first encounter group, the lower. Easy? That's all for naming.
So what if there are 2 double bonds in a ring?
We don't name that. Okay, if you see she asks is what if there are 2 double bonds? Okay, there are molecules, many molecules, a lot of molecules with 2 double bonds in the same structure. Okay, but we don't discuss that in this class. Okay, I'm not required. If another professor has no required, I am not. So you won't see that in your quiz, in your test. Okay, maybe homework you don't do it. It's fine. If you want, I'll show you later. Okay, they're called dienes. Okay, their name is called a diene because there are 2 double bonds. But again, is not the scope of this class. Okay, my class. Okay, any questions, guys? Good. Move on. Now, when you have a double bond, like this, it's very similar like you have 2 persons holding hands with 2 arms holding together. And you can imagine that, just think about you holding both hands, arms with another people, like a wrap up, tied up your both hands with another guy. What happens is what? You cannot dance as freely as what? Holding one hand. Okay, nobody dances with 2-hand hold, right? It's 1-hand hold, you can spin. Same idea here. If you have a double bond, you can imagine that rotation along this double bond axis is what?
Limited.
Impossible. Is that right, guys? Take a look. What happens if I rotate? Double bond is going to break. Is that right? So that's one very important fact about an alkene. Double bond rotation is frozen. It's 100% frozen. You cannot even twist a little bit. It's fixed. That means if I have 2 groups on the same side of the double bond, you can never rotate it to make it what? Opposite side. Do you guys see that? These are 2 groups on the opposite side. And that's 2 groups on the same side. There's no way you can change one from another by turning the double bond. Do you guys see that? And we call this isomer, what? Anybody remember? We talked about in chapter 1. Cis and what? Trans isomer. Okay, this is another case in which a pair of cis and trans isomer exist. Because of what? Rotation is what? Limited. Remember we said chapter 1, the ring caused the rotation what? Limited. That's why we have a pair of cis and trans isomer. Here the same. Rotation limited. Now you may wonder why the rotation. Of course, double bond is rotating, but the reason is, if you guys recall, a double bond consists of what? What bond? A sigma and what? And a pi. What is a pi bond? Like this. Is that right? Think about pi bond. The overlap has to be what? Parallel. Is that right? What parallel means? Straight side by side. Is that right? What happens if you rotate? These 2 p like a pillar will be not what? Will no longer be parallel. Do you guys see that? This is parallel. If you rotate, what happens? This 2p won't be parallel. So that means if you rotate a double bond, what happens is the pi bond is going to break. That's why double bond is frozen. You can never rotate anymore. And because of that, again, no free rotation, we have a pair of cis and trans isomers. Okay, cis and trans isomer. This is an example showing a pair of cis and trans isomer. Okay, very good example. The molecule here showing here is a simple molecule called butene. Why butene, guys?
4 carbons.
4 carbons. Do you guys see that? And the double bond is between what? 2 and 3. Is that right? 1, 2, and 3, and what? 4. So double bond between 2 and 3, we call the butene what? 2-butene. Does it make sense, guys? 2-butene. On these two carbons, you can assume or look at as or see it as there are 2 methyl groups on these 2 carbons. Again, they're on the same chain. It's one chain. But you can see it as there are 2 methyl groups on what? Each one of these 2 carbons. Do you guys see that? This 2-butene, these 2 methyl groups are on what? On the same side. Do you guys see that? This 2-butene, what happens is what? These 2 methyl groups on the what? Opposite side. Again, they're all the same chain. It's one chain. It's 2-butene. But these 2 groups makes a cis-2-butene and what? Trans-2. You can see that they're totally different. Here is the skeletal structure. See that? Double bond, 2 methyl on the same side. Double bond, 2 methyl on what? Opposite. Again, they're not methyl groups. They're part of the chain, but these 2 makes cis and trans isomers. Does it make sense? Okay, some of you always feel these are groups. They're not groups. All 4 carbons on the same chain. Okay, they just make. Let me build the molecule quickly for you. Okay, here in class as well. Okay, I'm not putting hydrogens, so what is missing will be hydrogen. Take a look. This is what? Cis-2-butene. Do you see that? 1, 2, 3, 4. 2 carbon on the same side. Cis-2-butene. And this is trans-2-butene. Do you guys see that? 1, 2, 3, 4. Okay, they're totally different molecules. Okay, totally different molecules. Right? Now, before we move on, alkenes, because of the double bond, you will have, or possibly have, cis and trans isomers. So how can we tell? How do we know if I see an alkene structures, if it has or not have cis or trans isomers? Here is a very simple way. Okay. If a carbon in the double bond has 2 identical groups or atoms, doesn't matter. If a carbon in the double bond, these 2 double bond carbon, any one, doesn't matter which one, has 2 identical groups or atoms, then you will not expect cis or trans isomers. Then the molecule would not have cis or trans isomers. Okay, for example, this guy, 2 hydrogens on the same carbon. You see that? This guy, 2 hydrogen on the same carbon, or 2 methyl on this carbon, the same, doesn't matter. As long as one carbon has 2 identical groups, then the molecule will not have cis or trans isomers. Does it make sense? The other ones will. Okay, for you guys, I will not ask you to tell me whether a molecule has cis or trans isomers. But if a molecule shows either is a trans or cis, you need to put the cis or trans when naming it. Does it make sense? If you miss that cis or trans, you miss half of the credit, pending your rest of the name is correct. Does it make sense? If you have a molecule naming, ask you, hey, can you name the following molecule? If it has shown cis or trans in the structure I gave you, you have to include cis or trans in your name. If you did not, you lose half of the credit if the rest of the name is correct. Is it correct? Make sense, guys? Okay, that's all I need from you. You know what is cis and trans isomer, and when you see a cis trans isomer, you can name it. That's it. Okay, you don't have to tell whether a molecule has cis or trans isomer. I won't ask you, but here is a simple way. If you have a carbon with 2 identical groups, it will have cis or trans isomers. Okay. What time is it? 9:30.
10, 12.
Well, what is our class? 9:30 through 10:45, right? Okay. Good. Next. Okay. After we study naming, the structure, very quickly, the physical properties of alkenes. Okay, physical properties. I only have like 3 lines here. That's why it's called very briefly. The physical properties of alkenes or cycloalkenes are very similar to those of alkenes. What does it mean?
No
Means if you know the physical property of alkenes, they are the same, almost the same as alkenes or acetylalkenes. So what are they? What is the physical property of alkenes?
Low melting and boiling
Low
point.
melting and what?
No solubility.
Boiling point. Low solubility or don't dissolve in what?
Water.
In water. Very good. Hydrophobic. And what else?
The more carbons on a chain,
The
higher
boiling point will increase as what?
Chain
The
length
chain length what?
increases.
Increases. Same applies to alkenes. If you want to ask alkene what is it, they're similar. We don't even compare between alkene and alkene. There is a difference, but we don't compare. We can assume these, we just mentioned these properties, these physical properties, are the physical property of what? All hydrocarbons. Does it make sense, guys? The same. We don't discriminate what's the difference between boiling between alkenes or alkanes. We don't. It's very hard to actually to discriminate these two. Okay, they're all hydrocarbons. Their physical properties are very, very similar. Okay, very similar. They're all existing together in petroleum. Okay, so again, that's why we said very briefly we talk about physical property. Next, okay, 30 minutes or less than 30 minutes, we're gonna study the most important part of this chapter, the chemistry of alkenes. Okay, maybe 80% of your quiz 2 next Wednesday will be on this topic. Okay, this topic. What reactions will happen for this alkene? Remember is that starting alkene, we have functional group. This is the functional group. This double bond, only 2 carbons define the whole molecule, is what? Alkene. So the chemistry of these molecules is the chemistry of what? These two carbons. Okay, these 2 carbons. So we're gonna study in the next 20-30 minutes these reactions. Even though I said it's very important, we're gonna spend 20-30 minutes, the reaction themselves can actually be summarized by 1 page. One picture shown here. Maybe you cannot verbally describe, but do you see what happens here?
Yes.
In a reaction, the double bond will break to become what? Single bond. And then after it breaks, what happens? Each carbon will add a what? A species. A or what? Or B. A, B are not real atoms, they're just something. So the reaction here, we call them what? Addition reactions. Addition means what? You're adding what? A and B to where? To these 2 double bond carbons. But in order to add A and B to this 2 and C's, you first need what? Break the bond. Not both of them, only what? Only one of them. If you want to know which one is broken, pi bond is broken. The sigma bond is very difficult to break. Okay, you don't need to know, but if you're curious, which one is broken? The pi bond of these 2 is broken for these reactions. Make sense? Do you guys understand the picture? It's very easy, right? Let's take a look. And by the way, here is another model picture to show you the further you can understand what's going on. The same. The previous one is a reaction, this one is using pictures. You see that? Double bond becomes what? Single bond. Then 2 balls, yellow and purple. They can be the same or different. They can be different species are added to what? Added to these 2 atoms. That's what we call them what? Addition reactions. Okay, before we move on, one thing very important in this chapter, or in the following chapters. When we talk about reactions in organic chemistry, most of the times, the reaction happens where? The functional group. That means what? The rest of the structure, you don't even touch them. What you do is what? Copy. If there's a cat over here, for example, I draw a cat connected to this carbon, here you still show that cat. Does it make sense? Because the reaction is happening where? Between these 2 carbons. Does it make sense? So that means the rest of the structure you copy. Don't change them. Does it make sense? This is very important. You're gonna do that. A lot of students, even you know how to work on these reactions. But when you draw the structure from reactants to products, you miss something else, which has nothing to do with the reaction. Like you go to a hair salon, you make some haircut, you come back with the arm missing. Like that, right? You don't do that. You come back with only something, your makeup, your hair, not missing something else. You're only working on the double bond. You're not supposed to lose a hydrogen or lose another carbon down there. Does it make sense? So please, that's why I ask you to form a good habit of copy the structure. Okay, so with that, let's take a look. What addition reaction we're going to study? First one is called hydrogenation. Okay, hydrogenation. Hydrogenation meaning adding hydrogen atoms. Okay, hydrogen atoms. Where do the hydrogen atoms come from? From this guy, H2, hydrogen gas. Okay, hydrogen gas. When you react with alkene with a hydrogen gas, take a look. The double bond becomes what? Single bond. And then you add a hydrogen on what?
Carbon.
Each one of these two carbons. We call that hydrogenation. Now take a look. After this, an alkene becomes what? Alkane. Is that right? Why? Because the double bond becomes what? Single bond. You're adding hydrogen. Now it's CC single bond now. You're getting an alkane. Getting an alkane. This reaction must be catalyzed by a precious metal catalyst. The reaction must happen on the surface of the metals. If you put these two, this is a gas. Normally alkene is a gas. If you put these together, they won't react. You need a catalyst. Nickel, palladium, the PD stands palladium. PT is platinum. Okay, these metal catalysts will provide a surface for them to react. Okay, for them to react. So that means
So is this why alkenes and alkynes are unsaturated, whereas alkanes are saturated?
correct. That is why these are called unsaturated. These are saturated. Now you can see that this is unsaturated compared to the saturated. Which one is missing? Why they're unsaturated? Because they have what? Less hydrogens on their structures. You guys see that? If I put more hydrogens to make an alkane, what is it called? Saturated. What did I do? Put hydrogen to saturated. Means what? The reason they are called unsaturated is because they missing some hydrogen. Why miss hydrogen? Because they have what?
A double bond.
Multiple bonds. Okay, double bonds here. Does it make sense, guys? That's why we name them unsaturated, saturated, because hydrogen. Okay, because hydrogen. Okay, that's the first reaction. Take a look at the examples here. Examples. Again, guys, this only shows what happens in the reaction. These are not carbon. These are something you can put anything. Like I said, if it is a cat, you leave a cat there. You don't change it. Okay, but here are some examples showing you. Okay, first step, like this molecule, 2-butene. Okay, this structure doesn't show cis or trans, so you don't need to worry about cis or trans. I first copy it to the right. Then change the double bond to what? To a single bond. Then add hydrogen to what? Each one of the two. This methyl is still there. This methyl is still there. Nothing else is changed except where?
Carbon.
Here. You guys see that? Okay, again, I can draw this step for you. Some of you may think this is silly, but when you have your reactions, I hope all of you can form the good habit of doing things like this. Okay, CH3 first. CH3. First, I copy to the right. CH3, CH, double bond, CH, CH3. Make sure I copy exactly the same. Then what? I follow what I learned from this reaction. If I see hydrogen and palladium, I know this is what? This is addition reaction, adding hydrogen. So I will do is what? I use my eraser to take the double bond out. Then I know these are the two carbons I'm working at. You can even mark it lightly, use a pencil. Then what? Add a hydrogen here, then what? Add a hydrogen here, there we go. This is not pretty, but it's correct. You get full credits if I give you a reaction like this. Okay, what does it mean pretty? Because this C now is become what? How many hydrogen on it now? 2 hydrogens, so you can simply change to what? To CH2 and what? CH2. This is prettier, but again, not required. Does it make sense, guys? So I can change these 2 metal carbons to what? CH2 and what? CH2, because that's what it becomes. Does it make sense, guys? That's not what I want you to do, okay? Again, if you're very good at it, that's fine, but I want you to form a good habit because we're going to study a lot of reactions throughout the semester. Okay, the bottom reaction is cyclohexane, hydrogenation. Which 2 carbons we're talking about?
1, 2.
Here, is that right? Doesn't matter, they're 1 or 2, they're these 2. So take the double bond to what? To a single bond, add a hydrogen here, add a hydrogen here. Why didn't it show that? Because I know now this carbon has how many hydrogens? 2 now. There was only 1 here. Now it has 2. Why? Because the double bond is what? It's gone. It's gone. Does it make sense? Of course, you can draw the structure like this. Hydrogen here, hydrogen here. That's fine. Okay, show, hey, I added hydrogen. That's fine. Again, not pretty, but correct. Okay, that's perfect, fine. That's great. You get full credit. That's beautiful already for me. You don't have to draw like condensed after the reaction. Good? Okay, next. Yes, like she was asking earlier. Okay, she was asking earlier. What if a molecule has multiple double bonds? These are the multiple double bonds molecules. If that's the case, if you want to put more hydrogen, put hydrogen on the double bonds. 1 double bond, you need 1 hydrogen. If you have 2 double bonds, you need what? 2 hydrogens. If you have 3 double bonds, you need what? 3 hydrogens. If you want to saturate them. Okay, again, you won't see these. Like I said, I just want to show you an example. And this is a very important industrial process when we're making artificial fat oil products. Okay, like we'll talk about in chapter 8 when we study lipids. Okay, if you want to change like vegetable oil to some creamy stuff, this is the industrial process, what they're doing, putting hydrogen on the fatty acid chains to make them saturated. Okay, we'll see those reactions, very similar ones in later chapters. Okay, that's first. Second addition reaction. Okay, second addition reaction, instead of called hydrogenation, these are called halogenation. Okay, halogenation. This word, halogenation, this word came from halogen. What is halogen?
7.
In your periodic table, the group 17, did I see that? The 17 column there, fluorine, chlorine, bromine, and iodine. We don't talk about the 18, this is radioactive element. These 4 elements are called halogens. They are similar. One thing is they all exist in nature as this. X2. X2 means what? Fluorine is F2. Chlorine is Cl2. Bromine is Br2. Iodine is what? I2. That's how they exist as something 2. And they can react with the double bond as well in a very similar fashion as hydrogen. Double bond becomes what? Single bond. You added a X on 1 carbon, add an X on a what? On another carbon. Okay, most times in halogenation, we're seeing is chlorine and bromine. Okay, we don't see a lot of iodine. Fluorine rarely see because fluorine chemistry is very unique branch of organic. We normally don't see fluorine. Okay, inner reaction wise. Okay, inner reaction wise. You guys see that? Very similar, right? Except now, instead of having 2 hydrogens, they have 2 what? 2 chlorine or 2 what? 2 bromine. And we call those haloalkanes or alkyl halides. Okay, the products are called. Okay, we call them halogens. Here, bottom is an example. Take a look. Again, what do we do first? Copy. Then what? Take the double bond out. Add a chlorine on 1 carbon, add a chlorine what? On the middle carbon. Again, you know which 2 carbons. These 2 carbons never has nothing to do with the reaction. Does it make sense? You only work on where? The double bond. The rest of them is again copy, copy, copy. Please don't lose an atom. Okay, like I said, somebody know how to do the reaction, but end up losing one carbon here. It's wrong because there's no way you can chop off a carbon, right? So I still can't give you full credit because I knew you probably know how to do it, but you end up with something not we wanted. They're totally different molecules. Okay, that's halogenation. Okay, halogenation. This picture shows you an experiment of halogenation. This is bromine. Okay, bromine. The color of bromine is very brick, dark red color. And when you put bromine with alkane, the bromine color will remain because they don't react. But if you put bromine with alkene, what happens is bromine is what? Is gone. Where do they go? They add to the double bond. So that's why you don't see bromine coloring. Okay, this is, you can watch, there are thousands of videos doing this experiment. Okay, on YouTube you can watch bromine with alkenes. You can see that when you drop the bromine into the test tube of alkene, the color will disappear right away. The reaction is super fast. It doesn't need any catalyst. Okay, doesn't need catalyst. Good, guys? Okay, next. In the previous two examples, one thing in common we studied about addition is A and B added to the atoms are what? When you add hydrogen, when you add chlorine, when you add bromine, both atoms added to the carbons are what? The same. Is that right? Both hydrogen are the same. Both chlorine what? The same. Okay, they're the same adding two carbons. You don't care which carbon gets which. But now, in the third addition reactions, we call that hydrohalogenation, meaning you're adding HCl, HBr, HI. What's different here is A and B now are what? Two different atoms, right? One is hydrogen, another one is what? Chlorine or bromine or iodine. Does it make sense, guys? But the reaction, how you perform or how the reaction happens is the same. The double bond becomes what? Single bond. You add a hydrogen to one carbon, you add hydrogen to what? You add hydrogen to one carbon, you add chlorine to what? To another carbon. Do you guys see that? All good? Okay, now there is a question, some of you. How do you know the hydrogen adds to this carbon? Can hydrogen add to that carbon, chlorine adds to that carbon? Yes, it could. But why we only end up with the same, with one product? Because they only have what? Two carbons here. No matter where you put the chlorine, you got the same thing. Trust me, you can try it. Let's try it over here. This one, you had a hydrogen on the first carbon. Let's say the first carbon. On the left carbon, I should say. Let's see if I add hydrogen on the right carbon, on the chlorine on the first carbon. This is what we get. Do you think these two molecules are the same? Yes or not?
Yes.
Yes or not? If you're not sure, name it. What name of this guy? Chloro what? Ethane. Why we don't call one chloro? Because there are only two carbons, right? This is definitely number one. So chloroethane. That's why someone, why there's no one here? Only two carbons. The one with chloro is definitely number one carbon. How about this guy? What would you name it? Chloroethane, right? This is number one carbon. They're the same. Okay, they're the same. There is a difference. Chloro can go here, chloro can go, but finally, eventually, you cannot tell. Why? Because you end up with the same thing. Does it make sense? But in some cases, this is the fourth reaction. Okay, fourth reaction, very similar to the third one. Instead of adding HCl, HBr, here we're adding what? Water. Water can be written as H and what? OH. And OH. So that means you're adding H and what? And OH. And very similarly, in this case, you cannot tell which carbon adds the OH, which carbon adds the H, because they're what? Only two carbons. Okay, these are very similar reactions.
So this would be named as ethyl alcohol?
This is an alcohol. We studied in chapter 3. Okay, the reason we call this an alcohol because that's what?
OH.
Of the OH function. Okay, we call that an alcohol. Okay, we'll study that in chapter 3, don't worry. But again, I put these reactions together. Do you guys see the difference? Or the similarity? The similarity is what? You're adding what?
Hydrogen.
Hydrogen and chlorine. Here you're adding what? Hydrogen and what?
OH.
On one carbon, another one on another carbon. And even though hydrogen can be added here or here, you end up with the same thing. Because of what? 2 carbons. Now, there is a case in which you end up with different molecules. For example, adding HBr to propene. This is propene, 3 carbons. The same, what happens is what? The double bond becomes what? Single bond. Bromine added here, hydrogen added what? Here. But, like I said, these 2 are different atoms. So bromine can either be added to this double bond carbon or what? This double bond carbon. You see this? These are the 2 double bond carbon, guys? Never now this carbon. Of course, there's no double here. You don't care. You copy. But these 2 carbons are different. Bromine can be added here or what? Here, of course, hydrogen the same, right? If bromine is here, hydrogen is here. If bromine is here, hydrogen is there. But in this case, you end up with 2 different products. The product on the left, bromine is on which carbon?
First.
1, right? 1, 2, 3. We call this 1 bromo propane. This product, bromine is on which carbon? Second, we call this what? 2 bromo propane. Of course, these 2 are apparently different compounds now. But out of these 2 compounds, this guy, the one in the red box, is the favored product. Favored means what? Most of the product will be this guy. In this particular case, you probably don't see this guy. Okay, sometimes you see both. This is major. Sometimes you, like this case, I doubt you will see anything if we run the reaction. Okay, in our class, if I give you a reaction like this, you don't need to show me both. You only need to show me the favored product. Do you understand? You may ask, so how do I know which one is favored? Of course, I'll show you. But again, if in a multiple choice asking you to choose which one of the following is the answers, you choose what? The favorite. If your reaction I show you on the screen ask you that, can you tell me what the product it is? You show me what? The favorite. Does it make sense? Okay, let's see. How do we tell which one is favorite? There is a Russian scientist. Okay, do I have a name here? No?
Yes, chemist. It's in the notes.
Your notes. I deleted them.
In the previous example, why is it favored? Like,
Yeah, I'm gonna show you.
Oh, okay.
Yes, yes. How do we figure out? I don't want to tell you why, because it involves organic chemistry. I want to tell you, how do you figure out which one is favored? Okay. There's a Russian scientist called Markovnikov. Okay, he observed a lot of reaction like this, and he found when 2 double bond carbons adding hydrogen and something, the hydrogen is always added to the carbon with more hydrogen already attached to it. Let me say it again. The hydrogen is always added to the carbon with more hydrogens attached to it. Take a look at this guy. The same as our previous page. These 2 are the double bond carbon. Is that right? These 2 are the 2 carbons. This carbon has how many hydrogens? 2. This carbon has how many hydrogens? 1. So if you run a reaction like that previously, the hydrogen will prefer to be added where?
H2.
Here. If hydrogen preferred to be added here, where does bromine go?
Second one.
That's one. That is why you got, sorry, this as the major product. Does it make sense, guys? There was 2 hydrogen here. The hydrogen prefer to be added here. So bromine can prefer to be what? To there, of course. That is how you figure out the favored product. And of course, this was developed by that guy, the Markinix guy. He see a lot of reaction. They always like this. So this is an empirical rule based on what? Based on experience. Later on, we proved he's right. Of course, we can explain it, but not in this class. Okay, all you need is based on your viewing of the structure. If you have 2 carbons that has different number of hydrogens, then the hydrogen will be preferred to be added to what? To the carbon with what? More hydrogens. Okay, more hydrogens. Then the other one, the X, can be chlorine, can be bromine, can be OH, if adding water, for example, will be added to what? To the other carbon. Does it make sense? Okay, we call that Mark's rule. Okay, the Mark's from his name. Okay, Mark-Nichols rule.
So this is true for hydration and hydrohalogenation.
Correct. Only for these 2 when you have different atoms. Now, I don't know if you have that page. Sometimes I have updated notes. But first, without copying it, take a look at these 2 reactions. And see if you can understand. Then I'll draw both on board very slowly and explain to you. And also, again, one more time show you when you have a reaction, how do you complete? What are the steps? What are your logic when you have a quiz and exams? What should you do on your scratch paper? Okay? So take a look at these 2 reactions. The first one, HCl. Second one, HBr. First, if you understand by yourself, even without me showing you, that's great. But I'll show you in a very slow way. All right. Anybody? Okay, you don't have to show me how. Do you guys understand? Any of you know why you got the product, or no clue at all? If you were given that in your quiz, you got it?
I think.
Good. Okay. Again, if not, that means you spend a little more time than others. Like I said, different of you click at different stages. But here, okay, let's take a look. The first reaction. Okay, this molecule first, if we name it, it will be called, anyone?
Methyl hexene. Yes.
Anything missing? 1-methyl
hexene.
cyclohexene. Okay, you have to tell me this is 1 because methyl is non-number. So 1-methyl cyclohexene. Good. Okay, this is the methyl group. Even I don't put CH3, it's the same. Okay, you guys good so far? First step, like I said, in any reactions in the future, what do we do first? Copy to the right. Okay, copy to the right. Please, guys, use pencil, copy to the right. Even you use your pencil in your test, it's fine. Okay, I encourage you to use pencil. Otherwise, you're going to be very messy on your exam paper. Okay, use pencil in your tests and quizzes. Okay, copy. And make sure you did copy. Nothing is missing. Arms not gone. Eyebrow is still there. Anything. Okay, next. This is addition reaction. We know addition reaction happens on what?
Double bonds.
Carbons. Where's the double bond? Here, is that right? So like I said, you can use your pencil to mark, put some dots on these 2 carbons. You know your eyes now will only be on where? On this carbon. The rest of it you copy, you know they're correct. Does that make sense? So, these are the 2 carbons I'm looking at. What do we do? First is what?
Remove the bond.
Remove the double bond. So I need to take it away. right? Again, you have two dots here. You don't lose it. You still know these are the carbons I'm looking at. I change this double bond to a single bond. Then I need what?
Add the chlorine.
Add the H and what?
Cl.
Add the Cl to these two carbons. Where should I add the H? It's based on what?
More hydrogen.
Which two of these two carbons have what? More hydrogen. Is that right? So let me ask you guys. These two carbons, how many hydrogen here?
2.
How many hydrogen here?
1.
One hydrogen here. Why? Because we see how many bonds?
Double.
1, 2, and what? 3 bonds. That means what? 1 you don't see. That's what? Hydrogen. So there was a hydrogen here. How many hydrogen here?
0.
0, because you see how many bonds? 1, 2, and what? 4 bonds. So it means no hydrogen here. So the hydrogen, this carbon has 1, this carbon has 0. What do? The hydrogen as where? Here. Chlorine as where? Here. Make sense? Hydrogen will be preferred to add to where? The carbon with more hydrogens. Of course, you can make it prettier. Okay, you don't have to show that hydrogen, just draw like this. That's the product. Okay, now this guy has how many hydrogens? Take a look. 2 hydrogen. Why 2 hydrogen? You had 1, you added 1. Of course it has 2 now. Make sense? This guy still has no hydrogen. Because 4 bonds, 1 is a chlorine. Does it make sense, guys? Okay, the same. Copy the structure. This double bond is very weird. Like I said, I'm just showing you all kinds of possibility. It's not actually part of the ring. It's bonded to one of the carbon in the ring, but the double bond is not in the ring. Okay, we don't name this compound. We don't name this compound in this class. Okay, but again, after you copy the structure, you put your eyes on where?
Double bonds.
On this carbon and what? This carbon. Again, double bond. You look at where's the double bond is, then the 2 carbons on the end of the 2 carbon are the ones you're focusing at. Right? First step is to what?
Removes the bond.
Remove the double bond. Again, my dots are here. I know where I should add stuff. What should I add? H and what?
Br.
Br. And I may ask where should I add H? Where should I add Br? These 2 carbons, this carbon has how many H? 2. This carbon has how many H?
1. 1, 2, 3, 1. 0.
How many?
0.
0 H. There are 4 carbon bonds. Do you guys see that? 1, 2, 3, and what? 4 means what? 0 hydrogen. There's no hydrogen on this carbon. So where should I add a hydrogen? Here. Where should I add the bromine? Here. Of course, I can make it prettier. I don't need to show that hydrogen. This one will be CH3Br. See that? One is a CH2, now becomes what? CH3, and also this carbon, you have a Br on it. First, again, you don't have to make it pretty. This is good enough. If I see this, I applaud for you. Okay, can you stop the recording?